So I'm mostly doing robotic machining and material removal, and our latest and greatest, most cutting edge sort of thing, the robotic surgery. So some details, just, we've been talking about robots this, robots that, and everything like that, but for anybody who's not familiar, this is kind of backing up a little bit more general overview of things. So why would you consider robots for material removal stuff and not, say, welding, where they're traditionally used? There's some new advances in technology that let us do more material removal applications than we were used to be able to do in robotic applications. Many of the subtractive technologies like oxyfuel cutting, plasma cutting, and gouging, and things like that actually would benefit from the 6 degree of freedom capability of robots. Normally you have an oxyfuel torch attached to gantry system and it can only do flat cuts. Maybe you put a beveling head on it and you can do beveled cuts or things like that. But in the real world, there are 3D surfaces that exist, and it would be nice if we could automate those processes as well. So that's where we're looking at and have some applications doing that more advanced cutting and material removal. Robots have different strengths and weaknesses compared to traditional machine tools. So it's important to understand those when you're doing these sorts of applications. Some of the weaknesses can be addressed with some new technologies and techniques that we can use on the robots. And I'll go over some of the weaknesses after I go over the strengths. So we'll cover all of that and some of the applications that we've actually done. So first off, why robots? Equipment cost. Robots just generally are cheaper than large machine tools. When you get into small workspaces and things like that, it's about equivalent. But on larger things and larger sizes, robots can be cheaper until you get into extremely large workspaces that you're working on. Work envelope versus the footprint of the machine. Any kind of traditional machine tool has to surround the object that you're working on. Robots don't necessarily. Robots reach out from a central space, so they're more flexible in how you can set these things up. Also less overhead, so it's easier to move parts in and out. And then the number of axes and positioning flexibility. Anything that you're doing past 3 dimensions on a machine tool costs you more because you have more motors to add than just the 3 linear motors. Robots already come with all 6 degrees of freedom that you could possibly want to use, and then you can add more on top of that. They have more flexible programming. Machine tools are usually G-code programmed. That's very, very restrictive. You can do some work offsets and things like that, but mostly it's you generate a program in a CAM package, and then that's what the machine tool runs. Travel speeds. Robots can usually travel faster than large machine tools, but there's some advantages there when you start talking about really large machine tools, but it's a little bit even, actually. You have more tooling options with robots, especially when you're talking about tool changing. If you get an oxyfuel cutting table, it's mostly just an oxyfuel cutting table. You can add a plasma torch to it. You can't add a deburring system to your oxyfuel cutting table. With a robot with nice ATI tool changers, you can add whatever sort of tools you want to, so you can do multiple operations in the one spot. And then robots are more tolerant to really terrible environments like thermal spray, things like that. Machine tools, you have to do way covers and everything like that. Robots, worst case is you just have to, sorry, Windows just wanted to restart. Okay, robots, if you need to protect a robot from a harsh environment, you just put a sock over the robot, worst case. So back on the cost thing, machine tools can be $1 million plus if you're talking about really, really large, heavy-duty ones. Robots, you can get up there in robot expense, but not that much. Machine tools come with your tool changers and your spindles. All the tool changer is usually just restricted to mill bits and things like that. Robots, you can add a spindle to it, and then you can add a tool changer, but you can have flexible tool changers, compliant tools, plasma cutting, whatever you want to put on the end of your tool changer. And for traditional machine tools, you're either going to pick a milling spindle or plasma or oxyfuel. You're not going to be able to switch between them. For a robot, you can pick whichever one is cheapest and best for your application, or do all three. So, and then on the work envelope side of things, this is kind of a traditional robot work envelope, and it reaches all the way around. But the robot's footprint is just right there. You do have to have guarding around it, but you don't have to have anything else aside from guarding around it. So it's just, they can be easier to integrate into a shop than actually trucking in an entire machine tool. All right, and then the positioning flexibility. This is actually a drill tap machine. So on this one, there's our extra axis right there. So we'll just have the 6 degree of freedom robot, and then if we need to get to multiple sides of the tool, we add the extra axis right there. Every robot in existence comes with the software to, not every robot, not UR robots. Many robots come with software to handle axes, additional axes, so you can tie a coordinate system to it and have all of that just be automatically coordinated. So you don't have to add that in to your machine tool capabilities. Most machine tools, if you're trying to add extra axes, many of them don't even necessarily coordinate that. It's just your CAM software has to handle the coordination on it. Okay, so tooling options, you can use a large number of material removal techniques. And you can do them all on one robot if you so desire. You can have drilling, tapping, milling, lapping, deburring, plasma cutting and gouging, oxyfuel cutting and gouging. All of those things. You could have a plasma torch on a robot to cut all of your pilot holes and then come back with your drill, with your tap and tap it, or you could just drill all the holes. All of that sort of stuff. So you can combine all of your material removal processes to most efficiently make your parts. This is the one that I specialize in. The flexible programming of robots is the main thing that we focus on here because we love robots. Machine tools, even your most advanced conversational machine tool interface, is basically you're configuring a couple of dimensions in a part or something like that, and then you run it. But it's still going to run a canned software, canned path. On a robot, you have a full programming language on the robot that you can do geometric calculations on. So you can bring in dimensions and things like that, and then have the robot actually examine the part and then adapt the program that it's going to run to the part, versus on a normal machine tool, you buy stock that's bigger than you need and then whittle it down till you get to what you want. On a robot, you can buy your finished part and then measure your finished part, because some parts have poor tolerances, and then adapt your program to match your cutting paths and your material removal paths to the part. So you can compensate for off-nominal parts which exist in the real world. So why not robots? It also comes down to the programming. Anything that you want to do fancy like, any advanced programming that you want to do is advanced programming, and you're going to need more than just a CAM package to do it, even more than just Robot Master or anything like that. So you will either have to hire or become an experienced robot integrator to do it. You do have teach and repeat as an option on any robot, which is good for simple operations, and if you add extra software packages, then you can make those adaptive with seam tracking and things like that. But eventually, if you want to do very advanced adaptive stuff, you're going to have to do some more complicated programming. There are certain tools that you can't run on a robot. Large diameter cutters and anything with large tooling loads, the larger the tooling load gets, the more difficult it is to run on a robot because robots have poor damping. A machine tool is ball screws on linear slides, so it's extremely stiff and rigid. So it's easier to control tool chatter and things like that. The robot stiffness comes entirely from servo drives. So it's harder to control chatter and tool loads affecting your path and affecting the robot. You can address some of the rigidity with your robot selection by picking a bigger robot, a stiffer robot, things like that. But the bigger and stiffer you get the robot, the worse your accuracy gets because it's servoing bigger joints. The joints are stiffer themselves, and it's just bigger linkages and bigger joints, bigger robot. So most robots have difficulty with accuracy. And it's not, every robot maker will quote their repeatability. Repeatability is usually excellent, but repeatability is you teach a point right here at the top of this A, and then you move over here, and then you come back, and that's your repeatability. And you can get like 0.2, 0.1 millimeter or better repeatability on robots. It's not my laser pointer. So you can get good repeatability. The problem and the challenge is usually absolute accuracy. So there's a difference between always coming back to that point and programming a point at 0, 0, 0 right here, and then programming a point at 100 inches over here, and actually having those be 100 inches apart. Absolute accuracy over the workspace is not usually good on robots because it depends heavily on exactly calibrating the angle and the lengths of all the linkages. So it can be addressed through mapping the axes, adding secondary encoders, having compliant tooling. There's also calibration that you can do on robots to exactly calibrate the kinematic model of your particular robot. And that's what I always ask for on my robots. I don't always get it because of budgets. That does increase the price a little bit, but if you do that, then you can get more accurate robot that's more reliable for offline programming. And now the interesting stuff. So some example applications that we'll be going through in plasma cutting, oxyfuel cutting, things like that. And some of this is going to be compared to kind of traditional machine tool applications of things and selection of which material removal process you want. So for plasma cutting, for instance, we have this nice chart of how expensive a cut is per linear inch versus how thick your part is. So plasma is very excellent at thin material, but eventually you reach a point where the plasma just is not capable of making the cut, at which point oxyfuel takes over because you just can't really do it. So oxyfuel is relatively cheap for, it's actually relatively cheap for most cuts, but suffers from accuracy problems and the fact that you can only cut steel with it. So plasma is good for certain cuts, certain materials. One application that we did, back to flexible programming, is we have a pipe profiling machine system that we're doing wizard-based programming on. So instead of running everything through a CAM package and building the program that way, the operator just puts in all the dimensions that he wants, similar to the flame cutting that Randy, the thermal spray program that Randy had, only for whatever sort of cut you might want to do on a pipe. The main advantage is that we just dump all of these dimensions to the robot, and then the robot can calculate the cut path for us. So we can generate an approximate cut path offline and then take all of that, dump it to the robot, and then we can have the robot modify the cut path further based off of what it finds about the geometry. So this is actually the profiling machine. Oh, we cut it too soon. So it's actually finding the beginning of the seam, the end of the pipe, and then offsetting everything from there. And then we're beveling the end of it, and then there's large amounts of holes that we'll cut and things like that. One of the things that was a challenge on this machine is this is actually cutting a large number of pipes, so a long length of pipe and then cutting parts out of that. And it's all resting on top of turning rolls. And the issue is that the pipe is not straight. So we actually have to touch off on the end of the pipe multiple locations to characterize how much it turns around and everything like that, and then modify our program to account for that. Even more challenging than that, so this one was relatively easy because it's a round pipe and we know more or less what the dimension is. The more challenging one was this one for cutting holes on the sides of a large shell that's sitting on turning rolls and would sag. So what we actually do on this one is it's a slow process of touching off on it. But we'll touch off on the sides to calculate exactly what the curvature is at that location, and then modify the cutting program to actually kind of unwrap it to make a round hole as opposed to a not round hole. I should have made these videos longer. And then versus cutting it by hand, so this was actually a stitched cut that is more difficult to do by hand. So it's a nice round cut, but we'll put stitches in it so that it can be knocked out later as opposed to just dropping in. So this one was the oxyfuel. This is actually the same machine as the first video. We just changed out to an oxyfuel torch because we can't get through this with the plasma torch. So that goes back to the flexibility in tooling. And this is actually coping the inside of that pipe nozzle. That's like 4-inch thick steel, so we just could not get through that. But the customer's original tooling for this, original robot for this, was like based off of cam plates, magic sort of stuff. So this one, we just took the robot and we can build that whole cutting program, slow down as we get to thicker cuts, speed up as we go to thinner cuts, and hold a much better tolerance. I was actually surprised when I came to their shop because we had originally considered it for just very large nozzle like this, and he put a 4-inch diameter part on the table and then cut it with the oxyfuel torch, which was an impressive amount of flexibility that I didn't know I had actually put in the system. But, so it was kind of hilarious seeing a giant oxyfuel torch cutting a part that was significantly smaller than itself. We've got drilling and tapping machines that we've done. I didn't cut this one. So we can approach the part from multiple directions. Tool changers. I should have cut this one more. Tool changers and things like that. So we can pick the different taps that we need, approach the part from whatever direction we need to, and drill and tap holes on it. Right. I'm going to cut that one short. Okay, so lapping. This is a lapping robot that we did where we really take advantage of the degrees of freedom of the robot. It's hard to make a machine tool that does this, so we've got a robot that'll do it for us instead. And it makes it easier to change things out because instead of having to change out a lot of tooling, you can just change the position that the robot goes to. You still have to change out the lapping plate, but you can change the position that the robot goes to instead of having to change a bunch of fixturing and positions of fixed slides and things like that. That's actually a compliant tool that we have on the end of it. You can see the spring. And then we also have a load cell in there to measure the force that we're exerting. And then deburring, we were actually ready to grind before KUKA was ready to grind. So that's a PushCorp compliant slide on there. It's only compliant in that long direction right there. You can see the travel limit right there. So we need the robot in order to use it because we have to keep that compliant direction perpendicular to the direction that we're actually engaging with the part. So we've done deburring operations as well. Right, to the more interesting thing. Knee surgery. Dan somehow observed a knee surgery and was shocked and appalled at the state of the art. So total knee arthroplasty is what they call it, and they basically take off the entire outer surface of your femur and your tibia, which that's upside down. So that's your foot up there at the top. So femur right here, tibia right there. They take the whole thing off, then replace it with metal, and then metal and some HDPE. The very, very original process was they would basically drill and bolt a jig to your leg and then use a Sawzall, a medical grade Sawzall, to cut all of these flat surfaces. And that was the state of the art. The current state of the art is more or less robotically placed jigs. There are literally robotically placed jigs where the robot will place a flat cutting jig and then the surgeon goes in with a saw to make those cuts. And then there's one system that uses a haptic control where it has force guiding to make sure that you don't exceed the boundaries of that cut that you're trying to make. But many of them have significant errors, which is kind of shocking. So they can be up to like 2 millimeters of error. And we thought we could do better than that. We decided to pick a KUKA robot for a couple of reasons. Why is that upside down? Johnny. Okay, I have no idea why that's upside down. That's probably my fault. At any rate, we picked the KUKA Iwa robot. It's a force-sensitive robot. It has torque sensors in all of the joints, so it can tell how hard it's pushing on, estimate how hard it's pushing on the end of the robot. It also has this redundant axis, which is very useful for where you're approaching things. So that's actually an extremely unusual motion for a robot to make. It's a collaborative robot, which means that it's safe to work around. It has a medical approved version, which was useful to us since we're trying to do a medical application with it. It's got the standard 0.2 millimeters of repeatability. The out-of-the-box uncalibrated accuracy is not excellent, but there are people who have done calibrations on it who can get it down to kind of 0.2 millimeter accuracy, which is what we're aiming for on the knee surgery robot. So we're confident that we can get the kind of accuracy that we want out of it. So the first step in the process is registration, where you have to locate the knee joint in space, because when they put you down on the gurney, there's no telling exactly where your knee is relative to the robot. And it's actually really important to the success of the surgery, because the distance between the final prosthesis surfaces is really important, because if they're too close together, then the joint is too tight and then your knee doesn't bend well. And if they're off an angle, then your knee bends crooked. So, and all that just depends on how you locate the knee originally. The current method is to use kind of camera trackers and probes. So you calibrate the robot to a camera, and then you calibrate the probe to a camera, and then you probe with that, and there's multiple back and forth that has to happen that has stack up issues on the tolerance and the error. We were considering non-contact probing with like laser sensors or things like that, but there's cartilage on the top of your bone, and CAT scans only measure bone. So visually, the only thing that you can get is the cartilage, but the plan is actually made against the bone, so you can't do that. So what we're actually going with is tactile force probing, where we use the force-sensitive nature of the robot to push through the cartilage and detect the bone underneath. So the robot, this robot right now is calibrated to poke at 2 pounds of pressure with that probe, and preferably not move the bone at all while it's doing that. And then once we get a whole bunch of points like that, we use some standard calculation techniques to fit those to the actual bone model, like so. So the green points were the original ones, and then all the colorful points are the ones where we've actually calculated the alignment of the bones afterwards. Then it's just calculating cut paths and actually running a machining operation, which is a normal sort of machining operation. Amazingly, a standard sort of ball end mill works well for this. So with our currently uncalibrated robot, we're getting about 2 millimeters of error in the alignment, which is kind of where the state of the art is right now. And that's with our uncalibrated robot. So we have good hopes that it will be better. And then the actual cut accuracy is of just how flat the cuts are and things like that is like 0.1 millimeter. So it makes good flat cuts that are just not necessarily aligned exactly how we want them. So once we calibrate the robot, we think that'll get better. And that's it.